Today we are going to do some Cartesian line integrals where we stay strictly in Cartesian. And also in about 2 seconds I'm going to stop dropping the accent. But before I do so, you go in the comments and tell me what accent I'm doing. Okay. So yeah, let's actually just start by drawing a picture. We go from -1 to 1. And notice that we have two paths here. We have C1, call this C1, and then we have a parabola, which is y equals 1 minus x squared. That, just kidding, just kidding. Y equals 1 minus x squared. This is C2, right? Remember, if it's a negative x squared, it is concaved down. And the plus 1 means it's shifted up 1. Okay. So we have C1 and C2, and those are two paths. But before we do anything with those, let's kind of identify a game plan here. I think for C1, it's pretty clear that there is no change in y because it's a flat line. So y is equal to 0, and we could say that dy is equal to 0 as well. Maybe, since that's equal to 0, we should let x equal main variable. And when I say we let x equal the main variable, that just means x is equal to x. So usually when I say something is the main variable, we're going to be converting this whole integral, which would usually be in terms of y and x, but we're going to try to make it just into x. And we're not going to try, we're going to do it. Okay. So if, well, this is the equation for it, by the way, then it's just x equals x. Then if x equals x, then dx is equal to dx. So I'm not even kidding, that's all it was. But before we, and since x is our main variable, before we start integrating, let's just state our bounds. It goes from -1 to 1. Okay, so now we can recreate our integral. So m is x squared minus y. And we'll just write the bounds. Dx, and n is 2x. And that's dy. Okay. So if this right here, let's convert this. It's a purely an integral of x. We're going to keep the x squared there. And if y is equal to 0, well, we'll just write y is equal to 0. This y goes away, so it's y dx. And then this 2x stays, it just chills. Keep it how it is, right? Nothing's wrong with it. What does this dy turn into? Oh, dy is 0, okay. So we just get this. And I'm going to get rid of the negative bound. This becomes x squared dx, which, and everyone likes this integral. Everyone likes polynomials. That's 0. That's 0. That was my whole little trick of why I'm times the whole thing by 2, which is equal to 2/3. Okay, but let's check my trick if you don't believe me. Oh, let's not do 2. If we were just to do this the way we said earlier, as x squared dx, 1 minus negative, not 1 minus, 1 to -1. This becomes x cubed over 3, 1 to -1, which would be 1/3 minus -1/3, which is equal to 2/3. So that's just a little trick, you know, just sometimes speeds things up. I usually do this when I just have one function. Not one function, it's always going to be one function. When I just have something simple. And you can always do this trick when you have an integrand, or I want to say product of the integrand that turns out to be all of the same degree. Okay, so just times the thing by 2 and you get rid of the other bound and turn it 0. Right. Okay, hey, and if you get it wrong, don't quote me on it. Okay, next one. C2. Okay, C2. Oh, look at that. We got a nice equation for it. Well, y is equal to 1 minus x squared. Oh, what does that mean? Well, dy is equal to -2x dx. Okay, I just had to shrink everything because I was running out of space. Okay, so there we go. Y is equal to that because it's literally says so. And dy is this because we know how to take the derivative of that. Okay, let's think, what should we make our main variable? Okay, oh no, look at that y, I don't know if I really want to use y as a main variable, it's kind of hard to describe. But if we describe this using x, maybe it's a little bit easier. Let's try it. So, let's write integral. Actually, let's write the fact that x is our main variable. So, again, we're going to have the integrand purely of x and integral with bounds of x. And what does x go? It goes from -1 to 1 again. Okay. So, let's write integral, which is 1 to -1. And, okay, so x, right, x is our main variable, so that x squared, it's just x squared. And then minus y, well, we're going to sub minus y for minus this crap here. And this is all dx, and dx is just dx. Okay. And then we would have 2x for n, which would be right here. And it's 2x, which is n, right? N is 2x, and dy. Okay. Oh, dy is this thing. Look at that. Okay. Like I said, you always need a simplified integral to get as many points as possible in your test, because it shows that, I don't know. What the hell does it show? It shows nothing. Okay. Negative, negative, positive, 2x squared. Okay, 2x squared minus 1. And then plus, what's this? Ooh, that's a negative 4x squared dx. And we gotta simplify it again. But like I said, you need to draw as many integral signs as you can when you integrate, because it makes you look a little cooler. Okay, so do this. Okay, 2x squared minus 4x squared. We get negative 2x squared minus 1 dx. And then we'll integrate. Actually, now we're actually going to do some integration instead of just rewriting things. Negative 2x cubed over 3 minus x from 1 to -1. And we're gonna factor out the negative just to make our life better. We get 2 over 3 cubed plus x. And it goes from 1 to -1. And since I love tricks so much, and I like trying to make the algebra as simple as possible, which is what you should always try to do. Remember I said we have oh, look at that, we have a polynomial. It's an odd polynomial. We have degree 3, degree 1. And we have a -1 down here and a 1 up here. So if we wanted to evaluate this and make this easier, we should times everything by 2 and get rid of this -1 and replace it with a 0. So I'm going to rewrite this one more time, which is 2 over 3 x cubed plus x from 1 to 0, which is going to equal to -2. I'm just going to put 1 in, which is 2/3 plus 1, which is equal to -2. Okay, 2/3 plus 1. That's 2/3 plus 3/3, which is 5/3, which is equal to -10/3. Okay, so we get that up there, and we have this up here. So that was our two paths. We had two different paths, and look at that. Yeah, that's our answer. What else to say?